Okay, so hi everyone. So thanks for this introduction and well for the already previous, two talks that introduced this topic very well. So this is joint work with people at EPFL in Switzerland and others at Columbia University and Cornell Tech in New York. Well, there's also one guy in Germany, but he was actually at EPFL while this was done. And so we built a system that we call FairTest, which essentially should allow you to take some machine learning model or even maybe just some data set and try to find these kind of weird biases, which we actually argue are bugs that you effectively want to search for and, well, try to resolve before journalists find them. So this is actually one story that hasn't been mentioned in the previous talks that was over the news as well a couple of years ago from Staples.com that switched prices based on user location. And this was kind of weird. I mean, it sort of seemed to be a kind of unintended side effect of their pricing mechanism that, well, depending on your race, you might live in different areas, you might get higher prices, and that's also something that some journalists found out, and it was quite embarrassing. Then there was this story from Google Photos that was already mentioned previously, so I'm not going to delve into it with more detail. I'll just mention that the way this was actually fixed, at least in a preliminary way, was to just remove the gorilla tag. So I guess that's one way of making sure that it doesn't get assigned to black people. Whether there's better ways to do this, that's, well, not something I'm going to get into too much detail, but it's a very, very interesting question that I think is absolutely not solved yet. And so, as I mentioned, our thesis here is that these are software bugs and that you should search for them and ideally try to remove them from applications with kind of the same way as we deal with, well, reliability, performance, and so on, which are, well, bugs that people maybe have a bit more experience with. But all the same, they negatively impact the way users experience your product. So you could think of how can we make sure that an algorithm will not suddenly assign different prices to people depending on gender or race or whatever. So this is kind of a correlation problem. And one thing you could do is, well, just say, well, I'm just not going to let my algorithm use gender. And as was previously mentioned, this might not work. I mean, you might have a feature that says what height you are. Well, if you're above a certain threshold, you're very probably a male. So if that feature is used, well, gender was never used in your system, but there's still some inference of gender or race or whatever else could be problematic. And this is essentially a problem of proxy variables that can come up. Another problem that's actually, there's been a bit of work in this area, as was mentioned by a previous question on this FAT-ML conference, so there's been quite a bit of work from people from the data mining, machine learning communities on these topics. And sort of some of the preliminary work, what they try to do is just look at a user base or data set as a whole and then just say, well, let's try to make sure that our algorithm doesn't well, do weird things based on, let's say, gender. So it treats men and women the same way. The problem is that even if you find out that that's the case, well, you could have subpopulations where this isn't. And that's basically a problem known as the Simpson's paradox. Or, well, you can view it in one way or another, but yeah, you could have combinations of features for which bad things happen, but when you view all of it at the same time, you don't have this problem. Incidentally, this example of Staples.com that I mentioned, what journalists found is that if you looked at the US overall, there wasn't really a big discrepancy. But if you looked at particular areas, so in particular states, this algorithm was actually applied and had, could have some weird consequences. And So what we found is that actually in a lot of applications, the sort of foremost challenge is to even just detect these problems. So that's what we found, what we saw with all these examples from things getting leaked by journalists. Well, these were actually problems that the developers weren't even aware of in the first place. And personally, I don't know about you, but I don't want to be the Google engineer who at 5 p.m. on a Friday gets a letter on his desk saying, well, we tag black people as gorillas, fix it. I'd rather have that be detected early on, and then, well, you can always see how you're going to fix this problem with, as I mentioned, well, one way is to just remove those tags that lead to problems. So I'm going to give a bit of a description, a bit of a more thorough description of how FairTest works and some of the algorithms that we use. There's actually nothing extremely fancy used here, which I would say is a good thing, because it probably means that it's going to be easier to use in a general setting. And so here we just consider some data-driven algorithm or application that's going to make decisions based on user inputs. Yeah, you can think of these as locations, clicks, or well then also sensitive attributes like your gender, your race, and so on. And the output could be a price, it could be a tag, it could be a decision whether you're hired or not, it could be your healthcare premium, whatever. And so FairTest is going to be used, is going to essentially consider this application as a black box and be used on the side, and so you will feed it with your user data and your application outputs, and it's going to essentially run a certain number of statistical algorithms to find these correlations in different contexts, different subcontexts of the user population, and generate a bug report for the developer. And a bit later on, we'll also mention some extra features that might allow some preliminary debugging of these issues that you might find. One thing I mention here is that since we're talking about bugs, you want to avoid false positives. This is kind of in any bug detection software, you really don't want to flood the developer with things that are not relevant. And so here, since we're talking about, well, correlations in data, we use traditional statistical techniques to measure the, well, how do you say this, whether a certain correlation is statistically significant and relevant or not. And then we rank all the results to give the developer sort of the most important findings first. And so, yeah, what this bug report will find is associations between a certain set of protected variables, so you can think of these as things you especially do not want to discriminate against, like gender or race, and your application outputs. Okay, so this I mentioned. So diving into this FairTest box in more detail, you start with this data, which ideally you'd want to be, well, that's always a problem you have in statistics, you want it to be sampled from the relevant user population. So this was mentioned previously with respect to this problem with the Google algorithm for the photo tagging. If they tested it internally and all the photos they gave it were of white people, well, the bug's not going to show up. So, of course, you want the data on which you're going to test your system to be diverse enough for issues to actually be found. Then we're going to split this into a training and a testing set, and we'll actually work in 2 stages, and this is because we want our results to be statistically valid to sort of avoid these false positives. So in the first stage, we'll use this training data to essentially find a large amount of potential bugs, so potential contexts in which your algorithm behaves badly. And then in a second step, we'll validate them to make sure that we only report those that are actually the most significant. And I'll go into the detail of this algorithm just in a second. It's actually based on a decision tree algorithm. I'll give some pointers as to why we chose this particular approach. And essentially what you measure is some form of association metric, and one feature of our method here is that most of it is actually completely agnostic to the type of metric that you're going to use, which means that it sort of generalizes to a large number of applications. And then you're going to generate a bug report, which, well, yeah, we're academics. We don't do fancy UX, sadly, so for now it's just text-based. But it essentially lists different contexts, so different subpopulations of your users, in which some strong association between gender, race, age, and your application outputs were found. So this is going to be the sort of main technical aspect of this talk. So internally, what we use is something that we call an association-guided decision tree. And the goal here is to find essentially clusters of users, so subpopulations of users, that are the most strongly affected by some form of bug. And essentially what we want here is that these clusters that we find, first of all, we want them to exhibit the most strong associations that we can find in our data set. But we also want these subpopulations to be interpretable. So you want to be able to say, people who live in Washington who have a college degree, out of these people, there's a high discrepancy in what your algorithm gives as outputs for men and women, or for white people and black people, and so on. And so this is why, this is mostly why we went for algorithms, decision tree-based algorithms. So at a high level, the way it works, you start with your global user population, and then you're going to try and split it into smaller subgroups based on the features you have, so-called contextual features, in order to maximize some association metric. And so you're just going to, in a recursive fashion, try to divide your population into smaller groups for which your algorithm is more and more unfair. So if you take as example this staples.com problem, you're going to start with the whole US population and then maybe try to split it up into different states and find that in certain states there doesn't seem to be a problem at all, in others there's a much bigger problem, and then you're going to delve even deeper into these particular states and find where really the challenge is and where your algorithm should be fixed. And then, yeah, you could continue this up to a certain level to get subpopulations that are smaller, more specific, but still very easy to define in terms of your features. So what we believe are advantages of this methodology is that, first of all, it's highly efficient. I mean, you just take your data set and partition it recursively to find these clusters that are that have high associations. And as I mentioned, you don't have to take any extra steps to make sure that your results are as interpretable as possible. And as I also mentioned before, this is kind of association metric agnostic. So the same way that when you use decision trees for classification, well, you can just decide whether you're going to use Gini impurity or some mutual information-based metric. Well, here, well, you can just decide on which particular association metric will be more suitable to the data you have at hand, and then at every step of the decision tree algorithm, just apply the relevant metric. So ones we've described in our paper and used in practice are some very simple binary metrics, sort of comparing output proportions for two groups. We then generalize this to a larger number of groups using mutual information, for instance, as a metric. We also used correlation for situations where you're dealing with scalar variables. So, for instance, finding a correlation between age and price or something of that kind. We've used logistic regression in cases where you have a very high number of outputs. So, for instance, to find which particular tags or labels of an image classifier are applied to black people versus white people, for instance. So we actually did some experiments on something of that kind. And well, you could also just decide that none of these are suitable for the problem you have and just plug in your own into this algorithm. One negative point that has to be mentioned with respect to decision trees is that it's, well, as we know, it's a greedy algorithm. So at every step you try to locally maximize some kind of criterion. So here the associations in some subpopulations, and well, you have no guarantee that the algorithm will necessarily find exactly all subcontexts in which your algorithm behaves badly. But, well, yeah, that's just something we have to deal with for now. So in particular, some bugs in your algorithm could be missed. So now I'm going to give a few details on an example application we considered. So here we took a healthcare predictor, which actually won a machine learning competition launched in 2012 called the Heritage Health Prize. This is essentially a boosted random forest type algorithm, I think. And yeah, so what the algorithm does is that it takes in some features about patients over the last few years, so their age, their gender, the number of times they went to the hospital, for what kind of treatment, and so on. And then it tries to predict whether in the following year a user will be readmitted to the hospital or not, or how many times. And, well, this could have applications, for instance, for, well, early diagnostic, or even for setting healthcare premiums or something of that kind. And, well, obviously, I mean, you can look at the data, but that's something you could probably guess for yourself. The older people are, the more likely they are to go to the hospital. So, in a way, we could say if we check what our algorithm does, well, obviously it's going to find that it's going to predict that older people will go to the hospital more often. And, well, that's not necessarily a bad thing. It actually should be doing that. What we looked at, which is in a sense more interesting here, is how the algorithm's error changes for people of certain ages. So in a perfect world, your algorithm would just have 0 error. Well, then it's a good predictor. That's good. But so what we found is that there's an extremely significant correlation between your age and how much error the algorithm will have on your prediction. And that's kind of troublesome, because that means that if you use this algorithm for, as I said, maybe setting your healthcare premium, then that means that essentially if you're old, the algorithm will just basically do things at random because it actually has no idea on how to predict things. It also means that maybe for early diagnostic, it's actually not going to be very useful because it actually misses, it does the most mistakes for people for which the algorithm would be the most useful. But that's, let's say, another topic. And so now one other thing we try to look at is how could you try to debug these issues, so kind of try to understand why these issues are happening and how they could potentially be fixed. And so one thing we have in our system here is a way to reason about confounding factors. So again, coming back to the earlier mention of Simpson's paradox, you find some weird correlation in your data, and then you try to ask yourself, but can this actually just be explained by this difference between people? A prominent example of this that most people will probably have heard of is the Berkeley graduate admissions data set that was collected, I think, in the 60s or 70s, where they found that there was a strong gender bias in admission rates over the campus. But then when you looked at individual departments, this association actually completely disappeared. It even reversed in some departments. So some departments actually were more keen on admitting women than men. And the problem there was just that the proportion of men and women that applied to different departments were very, very different. And women tended to apply more to departments that had very low admission rates overall. And so that's something that you'd like to detect. So if FairTest tells you, oh, we found this very strong association here between a patient's age and the error committed by your algorithm, well, you'd maybe try to understand why. And this is actually something that has a very weird implication on system design, because now you're essentially doing adaptive data analysis. So you're first finding some correlation, you're statistically validating it, and then you're trying to say, well, what happens if I do things a little differently? And well, if you do this too many times, well, at some point you're going to find stuff that's not statistically significant and you're going to be happy. But that's obviously something you'd want to avoid. And well, it's kind of an inherent problem of doing debugging in a statistic environment, is that you're kind of limited by the amount of data that you have and also by the amount of different experiments that you can conduct. And so, as an example of this, we come back to this healthcare application. And one thing we ask ourselves is, well, is this problem inherent? Is there just some variance in the target that we're trying to predict? So here, the number of days that the patient will spend in the hospital, that's just very, very different for older people than younger people. And so does this basically mean that any algorithm will tend to have this problem? You could think of this if for younger people, well, the number of days they spend in the hospital is a very, very simple function of some of the features you have, and for older people it's completely random, then any algorithm will essentially exhibit this. So what we did is we estimated this target variance for all our users, and then just split our data based on this new feature, so saying people that have for which this estimated variance is very, very high, others for which this is very, very low, then try to see what happens. And well, actually this weird correlation that we found nearly disappeared when we looked at people for which the variance was quite low, and so for which our algorithm actually had a very high confidence in its prediction. Sadly, for those people for which the prediction confidence was was lower, well, there still was quite a bit of a unfair association, but it gives some idea of how you might be able to understand what particularities of your data actually lead to these unfair situations. So some closing remarks. You can find our preliminary paper online. We describe some other applications that we've looked into. So we actually experimented with a image tagger on ImageNet, so trying to replicate this Google issue. So we took pictures on ImageNet of white people and of black people and, well, tagged them and then tried to see which tags were disproportionately applied to different races. And well, you find some weird results, like you find that it's much, much more common that white people get tagged with female underwear. That was actually a really fun part of my job. I had to look at these pictures to see if this was a ground truth or not, and it actually wasn't, sadly. And yeah, you find that black people are tagged with quite a few actually tags related to animals, not necessarily gorillas. There weren't enough of those in our data set for it to be statistically significant, but you still find some weird things. We also experimented with a recommender system, a movie recommender system, and also simulated this pricing system of staples using US Census data, and sort of found the same things that were given in this journalistic article, that, well, in certain states the problem was way more severe than in others. And so yeah, just some features that you can use in FairTest that I haven't given too much detail about are exploratory studies using aggression. So in the case of an image tagger, you have thousands of labels that can be given. And so if you have to test each of these labels separately to see if there's a disproportionate association, that gets kind of difficult. But using regression techniques, you can sort of test all of them at the same time and find which ones seem to be more related to different groups. I've also mentioned this adaptive data analysis problem. So this is something for which we have some preliminary support, and we're looking into more effective solutions based on some recent work from the differential privacy community. And so our system is built in Python. It sort of integrates with, I don't know how you pronounce this, SkyPy? Skippy? SkyPy, thanks. And yeah, it should, it's sadly not out yet, but it should come out pretty soon. And yeah, so as a takeaway, our goal is really to help developers of machine learning algorithms to test the algorithm that they built to try and find these problems before the journalists do. So, thank you.